n. All right, sorry I'm late getting started, but I think both of you were there in the last class and you realize I went way over and just have gotten back upstairs. Sorry about that. And it is warming up some up here, but it's not warming up very fast. All right. I believe we left off last time in chapter 4, which is higher order differential equations 4.1 preliminary theory and linear equations, and we're just wrapping up 4.1.2 which are homogeneous equations. All right, boy, I'm freezing. All right, here we have example 9 we started out last time. Here's three functions: y1 e to the x, y2 e to the 2x, and y3 e to the 3x. Now they just picked them very simple equations like this. They don't have to, there's no reason this one and that one's the same, that two and that two's the same, 3 and 3 are the same. They just happen to name them that way. And they say that satisfied the third order differential equations this, and I think we showed that last time. The question is, are these linearly independent equations? Okay. The way they determine that is by doing what they call the Wronskian. Okay. And if my hands were not so cold, I would pick up my pen and the pad here, and let me try to do this. Wait, y'all can't see that, can you? I don't know. That's the wrong thing. Okay. Sorry, folks. I thought I had the screen share on, but I did not. Okay. There's the book. This is what I've been talking about. I wish I would have said something. Okay. Let me move my things around a little bit because this is, they put the taskbars right in the wrong places. Now, last class I did not have access to see the text or y'all or anything else. This time I can. I don't know what the deal is on that. We're going to go to the whiteboard, so I'm not going to change this yet. So I guess let's just go straight to the whiteboard. Any questions so far? Sorry that I thought I was screen sharing, but I wasn't. Okay, let's move this over here, up and over, and this one to the left and up. My throat is so sore. Sorry about that. Okay. Now, here were our three functions. y1 is equal to e to the x. y2 is equal to e to the 2x. And y3 is equal to e to the 3x. Now, they just happen to have subscripts and superscripts being similar. Okay. Now, we've already verified that they do satisfy the third order equation. What we haven't done is verify that they are linearly independent. How we verify that is the Wronskian. The Wronskian for these three functions, e to the x, e to the 2x, and e to the 3x. And what is the Wronskian? The determinant of those three functions, e to the x, e to the 2x, and e to the 3x, on the first row, second row, the derivatives of each of those functions, which would be e to the x, 2e to the 2x, and 3e to the 3x. And the second derivatives, e to the x, 4e to the 2x, and 9e to the 3x. Now, how do we do that determinant? Repeat the first two columns. Okay, e to the x, I can't write, e to the 2x, e to the x, 2e to the 2x, and e to the x, 4e to the 2x. Okay, and then we do our down diagonals. That's a pretty ugly diagonal, isn't it? That would be 18 e to the, if you're multiplying exponents, you add the exponents. Same base, add the exponents. That would be e to the 6x. Okay, x times 2x would be x to the 3x times x to the 3x is e to the 6x. Go to the second lower diagonal here, downward diagonal, and that would be plus 3 e to the 6x. The third downward diagonal here would be a plus 4 e to the 6x. 3x plus x is 4x plus 2x is 6x. Now do our upper diagonals. I'm going to erase the construction lines here if I can get the eraser to cooperate now. It wouldn't last class, but it is now. Okay, let's do the upper diagonals. That's 2e to the 6x, but it's a minus. The next upper diagonal is a minus 12 e to the 6x. Okay, and the third upper diagonal is a minus 9 e to the 6x. Okay, so let's add our positives together. 18 and 7, 25 e to the 6x. Our negatives here are 21 minus 2 are minus 23 e to the 6x, and this comes out being 2 e to the 6x, which is not equal to 0. Therefore, these are linearly independent. Okay. Yeah, 2e to the 6x. I couldn't see where their answer was, but there it is. Now, what you can conclude from that, since they are all solutions, which we did last time, they're linearly independent of each other. You had a third order differential equations. We have three independent solutions. That forms a oh goodness, I can't think what the term they use for this, a general solution on the interval, and this is from all real numbers x. That would be y, the general solution, sorry, c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. That's your general solution for any value C1, C2, and C3. That would be, well, that is an ugly x there, and this one is missing the x here. Okay, 3x. All right. There's your general solution of that differential equation. All right. Now, that's exactly what they got back here on this, and I'm going to move y'all to the top now because that does less blockage. We haven't picked up anyone else, have we? Nope, just the two of you. No one else waiting. Hopefully someone else will show up. You're missing 3. Alright, I'm going to set this aside for right now, mostly because my hands are so cold they makes it cold. So here are our solutions. When we did the Wronskian between these 3 functions, we found that that came out to be 2e to the 6x, which is not just not equal to 0, it's never equal to 0 anywhere on the domain from negative infinity to positive infinity, because e to the 6x is always non-negative, okay, always positive. Wait, let me say that. Always positive. It can't be 0, and 2 times it, of course, can't be 0 either. So since this is these functions form a fundamental set of solutions, I couldn't think of that word, from anywhere from negative infinity to positive infinity, we can conclude that's your general solution of that differential equation right here with those 3 independent solutions. Now let's move on to non-homogeneous equations. Whereas before, any set of an equation like this, differential equation like this, equals 0, that's a homogeneous equation. When this right-hand side is not 0, then we have what we call a non-homogeneous set. So any function y sub p free of arbitrary coefficients. Remember, this can be written with arbitrary coefficients C1, C2, and C3 here. But anytime you have a differential equation with this is not equal to 0 on the right hand side, that's called a particular solution. Any function y sub p that is free of arbitrary parameters that does satisfy that with a non-zero function here, that's called a particular solution of the equation. For example, it is a straightforward task to show that the constant function y sub p is equal to 3 is a particular solution for the non-homogeneous equation y double prime plus 9y is equal to 27. Hold on just a moment here. Let me get Jesus here. All right, we got the first, the third, and the fifth here. My faithful 3 that come to all 3 classes just about, they're here. We're missing Ryan and Jemanuel so far. So hopefully they'll be coming in. Let me just make sure they're not in the wings waiting. Okay. Now in my first class this morning, one student, no, it was my second class today, one student said he was waiting for a long time trying to get in, and of course he never popped up, so I don't know what was going on. But my wife is thoroughly of the mind that everybody in the world is on Twitter now right before the election, and that probably our infrastructure is being stretched to the max. Tomorrow may even be worse, but anyway, we're going to try to still have it. All right, any questions? All right, for Jesus, we are in chapter 4, higher order differential equations. We just finished 4.1.2, which was homogeneous equations. Today, right now we're starting 4.1.3. Okay, now here's what we're looking at. Here's a non-homogeneous equation, y double prime plus 9y is equal to not 0, but something other than 0. Okay? So, let's go back to the whiteboard and verify what they just told us. Okay. And I'll take this off. This was the last thing we were doing, example 9, the second part of example 9. So I'm going to clear those drawings, and here we go. I think I'll leave the white space the way it is. It's not going to take that much room to do. Here's your differential equation. Well, here is a particular solution. Y sub p is equal to 3. Pretty simple, specific, particular solution. That is a particular solution for this equation. Y double prime plus 9y is equal to 27. Obviously not a homogeneous equation. What we're going to have to do is take a first derivative. Y particular prime would then of course be equal to 0, and y particular double prime of course would also be equal to 0. So this would be 0 plus 9 times 3 is equal to 27. That's obviously true. No matter, and it doesn't have a parametric or a oh goodness, what do they call it? Arbitrary parameter. I couldn't think of the word arbitrary parameter in it. You don't even want to put an arbitrary parameter. If you try to put an arbitrary parameter, it's not going to equal that. So this is a particular solution for that differential equation that has no arbitrary parameters associated with it. Okay? Now, I think we can go back to our textbook again. Okay, still got the 3 students here, right? Yes. So let's go back to, I'm finally beginning to warm up a little bit. Goodness, it feels so good. All right. Now, if you have, okay, it's a straightforward task to show that. We've just shown that, okay? If y1, y2, y3, y4, y5, all the way up to y sub k are also solutions for your homogeneous type, that was example 7, something like this one here, that would be up to y sub 3, okay, are solutions for that on some interval I, and y sub p is a particular solution for a non-homogeneous case, like equal 27 or something like that, then your general solution would be that linear combination with your arbitrary, goodness, my nose is itching, set of arbitrary parameters, okay? The C1, Y1 plus C2, Y2 plus C3, Y3, all the way up to C sub K, Y sub K. But then just add that particular solution. That will also be a solution for your particular solution 7, okay? Because these would equal the 0 case, and this one particular solution would equal this one. So obviously these add up to the 0, plus that one adds up to exactly what your differential equation is. Okay. If you think about it, that makes sense, because any linear combination of these is always going to be 0, and then the nonlinear, the particular solution would then always equal whatever that value is. Okay, so let's summarize that down here. If I could ever get my pen to show up, here is what we call the general solution, 4.1.6, the theorem 4.1.6, the general solution for the non-homogeneous equations. If y sub p, let y sub b be any particular solution for the non-homogeneous linear nth order differential equation 7, that's when the right hand side is not equal to 0, on some interval I, and let y sub 1, y sub 2, y sub 3, all the way up to y sub n, okay, because this is the nth order differential equation, be a fundamental set of solutions of the associated homogeneous differential equation 6 on that interval I, then the general solution of the equation on that interval is y is equal to c1 y1 plus c2 y2 plus c3 y3 plus all the way up to cn yn plus y sub p, where y sub p is a particular solution for the non-homogeneous case. Okay, now they do a little proof here, and they use your differential operators and all that kind of stuff, so I'll let you just read through that, but you'll see it's pretty much the same outline that we saw before. The characteristic solution shows up here and the particular solution there. This adds to 0, that adds to your particular solution. Now, we've just referred to right here the associated homogeneous differential equation. That's with everything just like example 7 here, except the right hand side for 7 is not 0, the right hand side for 6 is 0. Okay, now that's called the associated homogeneous differential equation. Okay, now to deal with that, here's a new definition, what we call the complementary function. Okay, we see in that theorem we just talked about that the general solution for the non-homogeneous equation consists of the sum of two functions. The first one is the homogeneous solution, okay, and then the second is the particular solution. The homogeneous part is called the complementary function, okay. That y sub c, this part here, c1 y1 plus c2 y2 plus c3 y3 plus all the way up to cn yn, that is the complementary, that's the the solution to the complementary function. That's the 0 function, and then the particular is the one for the non-zero part. So this is the complementary function, this is the particular solution. In other words, to solve a non-homogeneous differential equation, we first solve the associated homogeneous equation. That's when your right hand side is equal to 0, and then find any particular solution for the non-homogeneous equations. The general solution of the non-homogeneous equation is then the complementary function plus any particular solution. So y is equal to the general solution is y is equal to the complementary function plus the particular solution. The complementary solution, notice the sub c, all has those arbitrary coefficients c. The y sub p has no complementary, has no arbitrary coefficients, none. Okay, So let's do this example. General solution for a non-homogeneous differential equation. Okay, let's go back to our whiteboard and do what they tell us to do. I'm going to clear this off the screen, and this one may take a little more room, so I'm going to move y'all around a little bit. Okay. Goodness, my hands are still so cold, but it's warming up some. All right. This, by the way, is the top of page 128, or about middle of the page 128. Okay. Here is a particular solution. Now, I hate this now, but they do this every new chapter. They show us things without telling us how they got them. And then later they'll show us how to get them. I don't see any reason for doing this, but that's what they do. Here's a particular solution, rather bizarre one, minus 11/12. What a nice little number that is. Okay. Minus 1/2 x. Okay. It says is readily shown to be a particular solution for this non-homogeneous equation. Y triple prime minus 6y prime, I think that's a double prime, and let me get Jemanuel in here. Hold on just a moment. We got 4/5 of the class here. If we could just get Ryan here, we'll have a full house. Okay. Hopefully he will be coming. Yep, still only got 4 of you here, but I'm glad y'all are here. Okay, Jemanuel, goodness gracious, my hands are freezing. Chapter 4, Higher Order Differential Equations, 4.1, Preliminary Theory, Linear Equations, specifically 4.1.3, which is non-homogeneous equations, and we're on page 128, near the middle of the page, example 10. They say there is a particular solution for this non-homogeneous equation. Y triple prime minus 6y double prime plus 11 y prime minus 6y is equal to 3x. Okay. Now all we're asked to do is, by substituting that function, show that is a particular solution. Okay? So what we're going to have to do, of course, is do y particular prime. And that's pretty simply minus 1/2. Right? Because the derivative of a constant is 0. Derivative of minus 1/2. Oh, here comes Ryan. Perfect attendance today. Way to go, team. That made perfect attendance in my first class, missing just 1 out of 8 in my second class, and perfect attendance for the third class. Way to go. All right. Glad y'all are here. Ryan, we're in Chapter 4, Higher Order Differential Equations, Section 4.1, Preliminary Theory, Linear Equations, and we're specifically in 4.1.3, Non-Homogeneous Equations, and more specifically on page 128, example 10, near the middle of the page. Here was their suggestion of a particular solution, if I could get it to show up here, for that differential equation, and we're now taking the derivatives of this. Y prime is negative 1/2. Y double prime of that particular solution would of course be 0, which would also be y triple prime for that particular solution, because the derivative of a constant is 0, derivative of 0 is 0. Okay, so all these are both of those are 0. So y triple prime is 0, minus 6y double prime is 0, plus 11 times y prime, which is negative 1/2, minus 6 times y, which is negative 11/12, minus 1/2 x, okay, and this should equal, we'll see if that's equal to 3x. That's what it's supposed to equal. Okay, this was 0, that's 0. This is minus 11/2. I say halves and write 12ths. I don't know where that came. Oh, did I ever blow that? I meant to hit erase and I hit cancel or clear, and I don't know any way to get it back. So let's just go to where we left off. It was y triple prime minus 6y prime, y double prime, plus 11y prime, minus 6y equal 3x. Okay. Now, we had determined that y triple prime is equal to y double prime, y sub p, both of those are equal to 0. Y prime was equal to negative 1/2, and y was equal to negative 11/12, I believe it was, minus 1/2 x. Okay. And we were plugging those in. That would be 0. That would be 0. This would be 11 times a negative 1/2 minus 6 times a minus 11/12. Now let me make sure I am remembering that right. Yeah, I believe so. Minus 1/2 x. And the question is that equal to 3x? This will be minus 11/2 plus 6 times into 12 would be plus 11/2 plus 3x is equal to 3x. Yes, these two add to 0 and 3x is equal to 3x. So it's a pretty simple thing to show that this weird looking solution here, right here, that particular solution, I should have called it y sub p, and this is a y sub p here too, that, I think someone has music on, maybe Jesus, okay, that would give you that particular solution. Okay, now we also needed to be able to solve the homogeneous solution, and that was at y triple prime minus 6y double prime plus 11y prime minus 6y is equal to 0. Okay, that's the homogeneous part of this, and that would be called your complementary function. Okay, But they said back in example 9, which is just the previous page, we found out that those three functions that we did, and we did this last time, y1 is equal to e to the x, y2 is, that's supposed to be a 2, is equal to e to the 2x, and y3 is equal to e to the 3x. Okay, that these are all solutions to that. We did that last time. So our complementary solution, complementary function is y sub c is equal to c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. Okay, now with this being the particular solution, that one, this being our complementary solution, our general solution would then be y is equal to c1 e, it's supposed to be an e, to the x plus c2 e to the 2x plus c3 e to the 3x plus, well, actually minus, if I can get my eraser to work this time. Okay, minus 11/12 minus 1/2 x. Okay. Okay. Jesus, sounds like there's snoring in the background. Okay. If my dog were up here, I would think it was her, because that's about how she sounds, but it sounds like there could be something going on in the background. Anyway, there is your general solution for this differential equation, non-homogeneous differential equation. The first part, the part with arbitrary coefficients on it, that's your complementary solution to the homogeneous part, and then your particular solution for that particular part here gives you the second part. So this leads to a second superposition principle, if I can get to it. Okay, and I can, there it is. I can't get my cursor to show up. All right, I'm going to move this. I know somebody's microphone's on. I know Jesus is, but I can't see the other folks, so I don't know, maybe somebody else's is on too. I don't know. But anyway, sounds like I'm being a very good sandman here. Okay, so here's what we've just done. We showed that was a general solution, which is a sum of the complementary solution and the particular solution. So here comes another superposition principle. Okay, we've just used it. Here it is, written one more way. The last theorem of this discussion will be useful in section 4.4 coming up when we consider a method for finding particular solutions for a non-homogeneous equation. Let's just imagine that we have a bunch of these. Y sub p sub 1, y sub p sub 2, y sub p sub 3, all the way up to y sub p sub k. These are k particular solutions of a non-homogeneous linear nth order differential equation. That means you have something to the right of the equal sign that's not 0 on an interval I, corresponding in turn to k distinct functions, g1, g2, g3, g4, all the way up to g sub k. These are sums of functions on the right-hand side. Could be sums, okay? That is, suppose that y sub p sub I denotes a particular solution for the corresponding differential equation. Now, here's your homogeneous part. A sub n of x, y to the nth, plus a sub n1 of x, n minus 1 of x, y to the n minus first derivative of y, plus all the way up to a sub 3 of x, y triple prime of x, plus a sub 2 of x, y double prime of x, plus a sub 1 of x, y of y prime plus a sub 0 of x times y is equal to g sub I of x. So the y sub p sub I corresponds to this g sub I on the right hand side. And this I can be anywhere from 1 to k. Those are your k particular solutions. Okay? Now, if that's the case, then your overall particular solution is the sum of all those k particular solutions corresponding to these k g of x's here. That would be a particular solution for that homogeneous side equal to g sub 1 of x plus g sub 2 of x, the sum of all those k g's of x. Okay, so there's yet another superposition principle. All right, now they do a little proof here, well worth your time to go back and do the proofs. It's about the only place they really are using these L operators. They just shorten how they do the proofs. So I'll let you figure that. Okay, let's now go to example 11. Okay, now this is going to take a while, so I think we'll go to the whiteboard. Okay, and I'll clear the whiteboard. I'll try to clear the whiteboard. And I'll move Jesus and the rest of you down the right hand side here. Okay, we're now doing example 11 on page 129. Okay. Here's what they ask you to verify. First, verify that y sub p sub 1, two subscripts there, is equal to negative 4x squared. Okay? That is a particular solution okay, of this y double prime minus 3y prime plus 4y is equal to 16 minus 16 x squared plus 24x minus 8. Okay. Now, we got two more to go, but let's do this one first. Okay. We first need to show that is a particular solution for that differential equation equaling that g of x. Okay, so what we're going to have to do is do y sub p sub 1 prime, and that would be minus 8x. Okay, y sub p sub 1 double prime would be minus 8. Okay, so what we're going to do is plug that in here. Negative 8 minus 3 times this would be plus 24x plus 4 times negative 8 would be a minus this is so aggravating. Totally aggravating. No. Okay, I think I got it right that time. Plus 4 times a minus 4x squared, that's minus 16x squared. Okay, we'll look at that. Minus 8 plus 24x plus 24x minus 16x squared minus 16x squared. Yes, we verified that that is a particular solution for that differential equation. Okay, now just to keep from destroying that completely, let me see if I can get that to eliminate and eliminate and eliminate. Okay. All right. We verified that one. Let's do the second one. That y sub p sub 2 equals e to the 2x is a particular solution to the same left-hand side, but this will be equal to 2e to the 2x. Okay? Well, let's do that part. You need a y sub p sub 2 prime equal 2e to the 2x. Okay, you got a question? Okay, Jesus, I think your microphone's on. Okay, let's do y sub p sub 2 double prime, and that would be 4e to the 2x. Okay, now let's see what happens if we plug that in to the left-hand side of that differential equation. That would be 4e to the 2x minus 3 times 2, that would be minus 6e to the 2x plus 4 times that plus 4e to the 2x, and the question is that equal to e to the 2e to the 2x? Well, 4 plus 4 is 8, minus 6 is 2e to the 2x, and sure enough that is equal to 2e to the 2x. Okay, so we've got this one up here is a particular solution to that. This one here is a particular solution to that. Okay, now the third part, verify that y sub p sub 3 equal xe to the x is a particular solution to of, or whatever. Same left-hand side here. Y double prime minus 3y prime plus 4y is equal to new right-hand side 2x e to the x minus e to the x. Okay. Goodness, I'm losing it fast, folks. I'm going to have to pause just a moment here. I've drunk so much caffeine today and so much sugar. I'm feeling very lightheaded, but otherwise I'm not going to make it. Sorry about that. For those who weren't here before, we were in Georgia this morning at 5 o'clock when we got up, which was 4 o'clock this time, and we've been going at it solidly since then, so I am rapidly running out of gas, so to speak here. Okay, now what we have to do here, just like we had to do before, if I could get my pen to show up, there it is. Let's see, I think I've got everything I need from the book. Okay, what we have to do is do y sub p sub 3 prime. Now that's going to be a product mode. That'd be x first times derivative of the second plus the second e to the x times derivative of the first e to the x. And then a y sub p sub 3 double prime is going to be the same here, x e to the x plus e to the x plus e to the x. That's going to be 2 e to the x. Okay, let's plug those in here and see what we get. X e to the x plus 2 e to the x, that's the y double prime, minus 3 times this one, that would be a minus 3 x e to the x minus 3 e to the x, plus 4 times the top, that's plus 4 x e to the x, and ask ourselves, is that equal to this thing right here? Okay, well, let's see what we've got. Here is an x e to the x minus 3x e to the x. That would give you minus 2x e to the x plus 4x e to the x. That would give you 2x e to the x. So that part checks. Here you have a plus 2e to the x minus 3e to the x. That gives you a minus e to the x, and that checks too. Okay, and there we have it, that those are equal. Okay, oh my goodness gracious. I am so stiff and sore and tired. I'm just worn out here. Okay, now we have shown that the first particular solution works for this right hand side. The second particular solution works for that right hand side, and the third particular solution works for that right hand side. Okay, so we verified that those three particular solutions are correct particular solutions for those three sides. Then it follows from the equation 13 back in 4.1.7 that the superposition of those three, and I have very, very little room to write, So what I think I'm going to do is see if I can get to erase some stuff here. So let's erase this part here. Okay. I may leave the rest of it there for a minute. Okay. That y is equal to y sub p sub 1, that's this one, plus y sub p sub 2, which is this one, plus y sub p sub 3, which is that one. And this will be, I guess they just wrote them down, minus 4x squared plus e to the 2x plus x e to the x. Okay. That is overall your particular solution. That's also a solution of this differential equation equal to the sum of those. Now this will be minus 16x squared plus 24x minus 8 plus 2 e to the 2x plus 2x e to the x minus e to the x. Sorry, I ran out of room there. Okay, so that superposition of the three particular solutions, which I wish I could find my cursor. Where is it? There it is. There it is. That superposition of the three particular solutions will be a solution for this right-hand side. Let's see, that probably shouldn't be there. This right-hand side of the non-homogeneous differential equation. Okay? The G1, G2, and G3. Okay. Note if the y sub p sub I are particular solutions for your non-homogeneous differential equations, for each of those k g of x's that you would have on the right hand side, then the linear combination, now this time they put arbitrary coefficients in them. Okay, before they did not have those. Okay, but that's also a particular solution. But these arbitrary coefficients are not numbered the same way because it's however many g's you have, that's how many arbitrary coefficients you have, not how many, what the degree of your polynomial of your differential equation. Now it says before we actually start solving for homogeneous and non-homogeneous linear differential equations, we need one additional bit of theory. We're going to hit that first, and then we'll come back and do this. Now we don't have enough time to do them all, but let's do what we can. There are some remarks, and I think what I'll do is clear my slide here. I don't have to clear it yet, but I will, and go back to the textbook here and move y'all one more time here. Okay, now we just did all this example 11, and if you do have all these particular solutions, then any linear combination of them will also be a particular solution for when the right hand side is that same. Now you see, here's the difference here. These C's correspond to those C's. These are the, if you have, this is a G1, we'll multiply that by some arbitrary coefficient, and then you also multiply your particular solution by that same arbitrary coefficient. Multiply this one by some other arbitrary coefficient, and your CP2 will be that same C2 times the P2 will work. So these are not arbitrary constants. They are constants, but they're not arbitrary. We use the same symbol as we did before, but they're not arbitrary. They are specific to whatever the functions are down here. Okay. I wish they had used something else rather than the C's, because the C's bring to mind arbitrary. They're not. Now, this remark is a continuation of what we did before, so I'm not going to go into it a lot. But this is a dynamic system, dynamical system they call it, where T is your time dependence, generally, okay? And now instead of X's here, you have T's, okay? Everywhere you have that, and there you have a G of T. That's an nth order linear system, non-homogeneous because that G of T is not zero. The n time-dependent functions, and these are all functions of time, not functions of X, are the state variables of the system, okay? The y prime, y double prime, all the way up to the n minus first prime. Recall that their values at some time t give the state of the system at that specific time t. The function g is called the input function, the thing over here to the right, or the forcing function. The y of t of the differential equations is said to be the output or response of the system. Those are your solutions there, the y's. Okay. And I don't think I'll go through much more there. Just wanted to point out those terms. Homework exercises here in 4.1. We already did 4.1.1. Any of the odds, 1 or 3. If the answers are in the back of the book, do either one of those. Let me make sure that wasn't a student coming in. Nope, we got everybody here. Sorry. Okay, I was afraid someone had gotten bounced out. Then any of the odds, 5 through, I believe it's 11, if those answers are in the back of the book. No, 5 through 7, if 5 or 7, if those answers are in the back. Number 9, if that answer is in the back of the book. 11, if its answer is in the back of the book. Yuck. Okay. And 13 if its answer is in the back of the book. Then in 4.1.2, which we finished today, only had a little bit to go yet, any of the odds 15 to 21 if those answers are in the back, 23 to 29 if those answers are in the back, and 4.1.3, the ones we just covered now, 31 through 33 if those answers are in the back, 35, can't find my cursor here, 35 if its answer is in the back. Most of the time the discussion problems are not, but if you find any of those odd numbers that have answers in the back of the book, you can work through those discussion problems as well. Okay. Now, at least we've got 4 minutes. Let's get started on that one last thing they said we had to deal with. This is 4.2, reduction of order. Okay, now in the preceding section we saw that the general solution a sub 2 of x y double prime plus a sub 1 of x y prime plus a sub 0 of x times y is equal to 0. Now that goes back to the homogeneous case. The linear combination of some y, which is c1 y1 plus c2 y2, where y1 and y2 are both solutions, because this is a second order differential equation. These are both solutions that constitute a linearly independent set on some interval I. Now, beginning in the next section, 4.3, we will examine a method for determining those solutions. That's what we're getting at, finally, okay? When the coefficients of the differential equations here, the a sub 2, a sub 1, and a sub 0 are all constants. That method, which is a straightforward system exercise in algebra, we'll see that, it breaks down in a few cases, yields only a single solution, y1, of that differential equation. If that's the case, it turns out we can construct a second equation, y2, of a homogeneous equation, this one, okay? Even when the coefficient here is variable, provided we know a non-trivial solution, y1, of the differential equation. So if we can figure out the first one, then we can also figure out a second one. The basic idea described in this section is that the equation 1, this one up here, can be reduced to a linear first order differential equation by means of a substitution involving the known solution y1. That second solution y2 of this equation here is apparent after that first differential equation, first order differential equation, is solved. That's called the reduction of order, okay? Now, suppose that y1 denotes a non-trivial solution of that original differential equation. Let's see if we can get it all to show on the same screen. I'm not sure we can. Yeah, of that differential equation. Suppose that y1 does denote a non-trivial solution for that, okay? We seek a second solution, y2, okay, so that the set consisting of y1 and y2 is linearly independent on that same interval I. Now, if those two solutions, y1 and y2, are linearly independent, then their quotient, y1 divided by y2, is non-constant on I. Because if they were constant, they're dependent on each other. They're not. It has to be a non-constant on that interval I. So in other words, y2 divided by y1 is some new function, u of x. Now this kind of looks suspiciously familiar, right? Or y2 is equal to some u of x times y1 of x. Okay, just multiply both sides by 1. The function u of x can be found by substituting that value into the differential equation. That method is called reduction of order because we must first solve a linear first order differential equation to find u. All right, we're going to have to stop there because we've just run out of time. Unlike the last class where I went way over, and we are now in 4.2. We'll start with example 1. Okay, and let me erase what I have here. We don't have enough homework. We didn't do enough in 4.2 to have homework exercises, so we'll just end those with 4.1. Okay, any questions? All right, sorry I'm running so ragged on energy right now, but hopefully the rest of the week will get a little bit better. Any questions? Okay, then I'm going to stop sharing. Sick and tired of sharing. And unless there's some questions, I will end the meeting for us all. So take care. We will see you on Wednesday. And by the way, what is tomorrow? Election day, folks. Please, if you are qualified and can and registered to vote, please do so. If not, still cheer on the home team, okay? And hopefully get it done. Now, if the only time the three of you are in a class with mine tomorrow, if the only time it's possible for you to vote is during that class, please vote, okay? I'll record the lectures just like I've recorded today's, knock on wood, and that way you can pick it up get back as soon as you can and join the class again. Any questions? All right, I'm going to end the meeting for us all. Take care. We'll see you, 3 of you tomorrow, all of you on Wednesday. Good deal. Bye-bye.